Okay, welcome. So, what did we learn in the last class? We had ended the last class with the introduction of breakdown. I told you that breakdown can happen in PN junction diodes in reverse bias because primarily of two main mechanisms, tunneling based breakdown and avalanche breakdown. What physically happens in breakdown is that suddenly the current will start increasing. The reverse leakage current, which is very low, will suddenly start increasing at some large reverse voltage. So, something is happening which is leading to that. Okay, I told you there are two reasons now. So, today we shall discuss, we will start the discussion in those two reasons why a device can break down. It is very important practically to understand breakdown and know what the limits are, because you typically want to operate the device not near the breakdown, less than breakdown, okay, because if the device breaks down then you will lose the performance, right. So, you do not want the device to operate near breakdown. Also the breakdown, if the breakdown is for example minus 20 volt, that sets an upper limit as to the extent to which you can use the device. So, you cannot use the device at minus 25 volt for example. So, that is very important, right. So, we will come to the whiteboard and we will start understanding the two mechanisms one by one. Okay. So, in a PN junction breakdown, could happen because of two reasons. One is tunneling and one is avalanche, right. So, let us come to tunneling first. What does tunneling mean? At very high field, okay, at very high field reverse bias, at very high reverse bias I can say, which also gives you a very high field, by the way, a very high reverse bias also gives you very high field, right. So, how will the band diagram look like? You have, it will look like something like this at very high reverse bias. So, your reverse bias is very large, depletion also is sort of large. Okay. So, this is the whole quasi Fermi level EFP, this is the electron quasi Fermi level EFN. So, what happens is that if you have a very high doping of relatively high doping of p side and relatively high doping on the n side, then this depletion is generally narrow, although you are applying a reverse bias and trying to increase it, but the depletion is narrow. And what happens is that this becomes a thin barrier, and electrons that are there are many electrons in the valence band, right. The valence band is filled up with electron, they will see empty states here, these are empty states, these are empty states in conduction band. So, they can tunnel across the barrier, they can tunnel across the barrier, and that because of the tunneling, then this will happen at high field only. So, and that tunneling across the barrier will suddenly lead to a large current, okay, suddenly lead to a large current, and that is called tunneling current, okay, and that is called tunneling breakdown, tunnel breakdown, or it is called the Zener breakdown, because Zener is the first person who proposed it or found it. So, it is called Zener breakdown or tunneling breakdown. So, high field, this electrons will find a lot of empty space, they will tunnel essentially, okay. And this happens when your p and n side are sort of little highly doped, these are sort of highly doped. And if you look at this again, if you look at this, let me again take a new page actually. So, it is like that, right. So, it is actually, there is a triangular barrier that it has to overcome actually, okay. This is sort of the triangular barrier, okay. This is sort of the triangular barrier, okay. This is the barrier that it has to overcome. This barrier is the barrier which the electrons here will have to tunnel to reach to the other side, okay. So, it is a triangular barrier, and there are equations to calculate what is the current that you will get here. It is a complicated looking equation, you do not have to memorize it, but we just have to understand the physics, and that is that the electrons can tunnel from one side to another side across this barrier. This actually, this looks like a triangular barrier, there can be different kinds of barrier, this looks like a triangular barrier, and I am assuming that you know what is tunneling from your high school physics. Tunneling is when you have a potential barrier. So, this is a potential barrier, if electrons are here, it can still tunnel from one state to other state through the barrier, which is not possible in a real world. It depends how much can tunnel, it depends on the height, lower the height more is the tunneling, and also it depends on the thickness of the barrier, lower is the thickness, thinner the barrier is, more is the tunneling. So, that is why I said this barrier will be thinner, if this barrier will be thinner when the doping is high. So, it can tunnel more. So, this is called tunneling. Typically tunneling occurs at a reverse bias breakdown, when the tunneling breakdown voltage is typically around 4 times the band gap. So, for example, if silicon is band gap is 1.1 electron volt, then the tunneling based breakdown might typically occur at around 4.4 volt. It can vary a little bit, but this is typically the around this value you might expect a tunneling based breakdown if it is a little relatively highly doped, okay. because of the high field and because 4 times the band gap is little high, you know, because you are dropping 4 times the band gap essentially. Okay. So, secondly, the avalanche breakdown comes, and avalanche breakdown is even more important actually. Avalanche breakdown is more common breakdown, and many of the devices actually suffer avalanche breakdown only. So, what happens is that, and for this avalanche breakdown you do not need to have a high PN doping, you even do not need to have any doping sometimes, you do not even need to have a thin barrier, it is a different kind of breakdown mechanism. So, what is happening is that at high field, okay, at high field in a reverse bias voltage what happens? In a reverse bias, this is a p type, right. So, any minority electron that comes here, it will be immediately swept away here, right. So, at very high reverse bias, at very high I will say VR, which means the very high reverse bias, this field also increases, no. So, the electron will be accelerated very fast, this electron that is coming will be accelerated very fast or very high, you know, accelerated very fast, and it will acquire high kinetic energy. This electron, because it is accelerated fast by the field, will acquire very high kinetic energy. So, what will happen is that the electron, because by the virtue of its high kinetic energy, it will knock out an electron from an atom and a neutral atom. It might knock out an electron from a neutral atom and it might create an electron hole pair. If it knocks an electron out, it might create an electron hole pair. So, an electron that was coming, it strikes one atom, it creates an electron hole pair, okay, because it was too energetic. It was too energetic because it has a lot of kinetic energy, that is because it was accelerated fast by the very high field, and this electron that is formed here will now get accelerated. The second electron that is formed will now get accelerated and might knock out another electron hole pair and create one electron hole pair. So, this electron itself might create one electron hole pair. Similarly, the hole that was formed also might accelerate and and that hole also might also create one electron hole pair, because that hole will be now highly energetic. So, that hole will also knock out an electron or a hole from a semiconductor and it will create an electron hole pair. Of course, the electron has to travel more distance here, the hole has to travel less distance here. So, this is like an electron initiated process. It is an electron initiated process. Sometimes there can be hole initiated process also. You know, if you talk about the holes, this is n type, the hole coming from here, it will knock out and create an electron hole pair, that electron will again accelerate, knock out, another it will knock out, it will keep going. So, it might be hole initiated, this might be electron initiated process, but you know it creates one electron will create electron hole pair, one electron again will create the secondary, this will create, then this will create 2. So, it will multiply like an avalanche, it will multiply like an avalanche, right. It will multiply like an avalanche, and suddenly and very rapidly in a very smaller time frame, this will lead to a huge number of carriers that will keep flowing this side, because they are knocking and creating 2 to a factor of 2, right. So, this avalanche will multiply like an avalanche, rapid increase in the electrons, and this leads to a sudden surge in the reverse bias current, it will lead to a sudden charge. So, this is called your avalanche breakdown, okay. This is called your avalanche breakdown, and there is a critical field at which it will happen. Typically, it will happen at a reverse bias voltage greater than 6 times the band gap. So, silicon band gap is 1.1 eV. So, the avalanche breakdown will happen at a voltage or reverse bias voltage of more than 6.6 electron volt at least, okay. So, you know the avalanche is basically this rapid multiplication of carriers, because they gain kinetic energy and keep producing the electron hole pairs in a very rapid succession, okay. And so, associated with this there are 2 terms, one term is called alpha n, one is called alpha p. These are actually called the ionization coefficient, impact ionization coefficient of electrons and holes respectively. This is electron, this is hole, impact ionization coefficient. What is impact ionization? This term impact ionization is used actually to describe this process. When the electron gains sufficient kinetic energy and it knocks out the carriers and produces one electron hole pair, that is the rapid creation, we call it avalanche creation, that is happening. Technically, it is called impact ionization, okay. What is happening is that electron, by virtue of higher kinetic energy, is impacting, you know, it is creating an impact on another atom and creating an electron hole pair. So, it is ionizing that electron hole pair. So, we call it impact ionization. We call it impact ionization, and impact ionization, you know, the impact, we have an impact ionization for electrons, we have an impact ionization for hole, and this way the impact, and this is a coefficient by the way, constant. This impact ionization coefficient is defined as the change of electron concentration. For example, it is electron, the change of electron concentration. So, delta n, okay. What is the change of electron concentration with respect to position? because you see, you know, this is an electron and it rapidly is creating one electron hole pair, again it is coming electron hole pair, it is creating and going, no. So, what is the change of the excess carriers you are actually generating because of this impact ionization with respect to the position, this is position, right. This whole thing divided by the total electron at any point, this is your impact ionization coefficient, and the way they are multiplying, the carriers are actually creating and multiplying, no, they are creating and multiplying, there is a multiplication factor, there is a multiplication factor defined as m. Okay. This multiplication factor actually tells you how many carriers are getting generated and what is the rate at which they are generating and so on and so forth. So, multiplication factor gives you an idea how rapidly they are multiplying and so on. So, multiplication factor is defined as 1 by 1 minus integration of this alpha n, because this might keep changing with distance, into dx over this area over this period, this w over this w, the depletion over which it is, because only the depletion will have a higher field, there is no field here. So, there is no point considering here, and the moment this integration goes to 1, your m tends to infinity, and that is when your avalanche breakdown actually takes place. Matlab now one electron that is injected can virtually lead to an infinite number of electron hole pairs by the time it comes out here, that is what it means. So, when m tends to infinity, it is called avalanche breakdown, and that means that one electron that you are injecting can virtually lead to an infinite number of carriers that are there, and that happens at a certain voltage, right. And so, there is a field, there is a critical field for each material, and the critical field is the electric field at which this avalanche will typically, this avalanche breakdown will happen. This critical electric field is called, say, F critical, I will call it electric critical field, and this depends very weakly on the doping concentration of the material. It is very weak dependence. So, I can say that this is fairly independent of the electric field. For example, in silicon this is probably close to around 400 kilovolt per centimeter. So, at the field of 400 kilovolt per centimeter, that is electric field, your silicon might start giving you avalanche breakdown. This is called critical field, and then there is a voltage. The breakdown voltage will depend on the depletion width, of course, it will depend on the depletion width. So, the breakdown voltage, for example, in a p-n junction, if you recall, if you apply the, this is x, for example, this is 0, this is w n, this is minus w p, your field profile was given by something like that, right. This is the maximum field, which is f max, we call it, that f max, the maximum value, that is q n d w n by epsilon not epsilon s, the same thing as q n a w p epsilon naught by epsilon s. For a material to work at the limit of breakdown, the maximum this can be is actually F critical, which is defined in a material. Each material has its own critical field, okay. And the voltage that it will block is the area under this triangle actually. The area under the triangle is half into W, which is the total thing, into F max, which is your F critical. This is your V breakdown. So, if you know the breakdown, if you know the critical field, if you know the depletion width here, then you know at what voltage breakdown it will happen. So, for example, silicon has a critical field of around 400 kilovolt per centimeter, and suppose the depletion width that you have in a semiconductor, the depletion width that you have in a semiconductor here, suppose the depletion width is given as, say, 1 micron, which is 1000 nanometer, or 1 micron, the same thing as 10 to the power minus 4 centimeter, okay. So, then the maximum breakdown voltage that you can block is half into 10 to the power minus 4 centimeter into this 400 kilovolt per centimeter. So, centimeter gone, this is 10 to the power 3, this is 10 to the power minus 4. So, this is 10 to the power minus 1, this one goes here 20 by 2. So, this is 20 volt. So, the breakdown voltage is 20 volt. You can block 20 volt with a depletion region of 1 micron or 1000 nanometer if your silicon's critical field is 400 kilovolt per centimeter. Okay. That is the breakdown voltage you can essentially block. Okay. But again, of course, if your material has a higher band gap, for example, gallium nitride has a band gap of 3.4 eV. So, the critical field of gallium nitride is 3 megavolt per centimeter, that is a much larger voltage than silicon. So, you can drop much larger, actually you can block much larger voltage. So, then for the same depletion region 1 micron, your breakdown voltage that you can block in gallium nitride p-n junction with the same depletion will be half into the depletion, which is 1000 nanometer, into 3 megavolt per centimeter is 3000 kilovolt per centimeter, which is roughly 9 times more than this. So, if silicon you can block 20 volt here, right, with gallium nitride you can block around 180 volt. So, which means you can use the gallium nitride PN junction to do much higher voltage blocking. So, for high power electronic devices or the devices that need a lot of voltage to be blocked, you can use gallium nitride with the same device dimension compared to silicon. That is why for emerging power electronics, like where you need to do all this power conversion blocking high voltage like electric vehicles and other things that are emerging, gallium nitride is a more suitable material because it can block larger voltage than for example silicon. So, power electronics where you need this power switching and large voltage blocking capability, gallium nitride devices are now getting established as superior to silicon because this is a wider bandgap material. There are other wide bandgap material also like silicon carbide and so on. So, those are established to be much better at blocking voltage. So, this comes from this breakdown kind of a thing. Okay. So, the breakdown of a material defines the limit to the breakdown voltage you can operate the device at, and that sets a limit to the technology also. Like if you look at an electric vehicle, you need to charge the vehicle, and that onboard charger probably will need 3 kilowatt power to charge it. So, it will have some 600 volt for example a bias that you have to block when you switch. So, it depends on the material, it depends on the PN junction properties whether you are able to block that 600 voltage. If not, then you have to go for a very slow charging over a long time. So, those are the things that are important in real world devices, how PN junction and how the blocking of a PN junction is very critical to that. Okay. So, this is about the breakdown that we have studied. And finally, remember that the breakdown is of course larger for larger bandgap material because the critical field typically is higher for a higher bandgap material. Okay. The final thing that we remember is the capacitance voltage. What does capacitance voltage actually mean? So, you have a PN junction, as I keep telling, there is a charge here, there is a negative charge here, there is a positive charge here, but this is a depleted region. There are no carriers there, and this p type has holes. So, this is highly conducting for example, this is also electron. So, this is highly conducting. So, it looks like these are very highly conducting layers that are sandwiching or that are wrapping around an insulating layer, because there are charges here in this layer, but it is insulating because there are no free carriers, there are no mobile carriers in this region. So, this is a depleted region. So, essentially it is like you have a conducting region, and in between you have a depleted region like an insulator. So, this is a capacitor, and this capacitor has a capacitance given by area, which is the area of the cross sectional area times epsilon naught epsilon s by this depletion width W. Of course, I want to express normalized capacitance. So, which means I will express take the capacitance here, area here, and I will take it as a normalized capacitance in the units of farad per centimeter square. Typically, the unit of capacitance is farad. I am normalizing it to the area. So, it is area non capacitance per centimeter square. Okay. This is your formula, but you can actually derive this also in a more complicated way, and you will still end up getting this. A capacitance actually, and this is by the way called this is called the depletion capacitance because it is corresponding to the depletion region. It is called depletion capacitance, or it is also called junction capacitance. The reason is because this is corresponding to the junction here, this also corresponds to the depletion region here. So, there is charge here, there is a depleted region here. So, it is a depleted capacitance, it is a depletion region capacitance. You can think of it as like there is a highly conducting metal, there is a metal, actually it is not metal, but there is a metal, and in between there is a dielectric, this is depleted dielectric. So, essentially that is like a similar kind of a thing. So, it is a depletion capacitance or a junction capacitance, and when you use the diode in different circuits and other things, this depletion capacitance, because there is a capacitance, it can lead to RC delay for example. There is always a resistor associated with it, that our resistance time capacitance can give you a delay, make your circuit slower. So, these are very important things, and you can actually derive this value of this capacitance by going the more traditional route. For example, this is your p type, n type for example, there is a depletion region here, I call it W. So, essentially the capacitance is defined as the small change in the depletion charge. What is the charge stored here, which is d, which is the small change in the charge stored there, I will call it q delta d, matlab the depletion charge, divided by the small change in the applied voltage VA. So, if I apply voltage, okay, at small change in the voltage, a small change in the voltage, whether it is forward or reverse, but typically we talk about reverse bias only, but even typically we talk about in the reverse bias only. So, okay. So, a small change in the voltage that you are applying delta VA can lead to a small change in the charge that you are storing. The ratio is called the capacitor. See, if you increase this, suppose you are applying a voltage say minus 3 volt, you are increasing a small amount from minus 3 volt to minus 3 say 1 volt. What will happen is that this depletion that was there will slightly increase with reverse bias it slightly increases, no. So, the moment it slightly increases, the delta, some extra delta has come. So, what is the change in the charge stored now, because it has slightly increased, there is a slight more increase in the charge that is storing. What is that ratio with respect to the voltage that you are changing, right. So, what is the actually charge that you are storing? The charge actually that you are storing, if you look at each of this block, is actually Q say Nd Wn which is the depletion on the n side divided by epsilon and epsilon s. I can write this as Q Nd by epsilon naught epsilon s, and the Wn can be written as Na divided by Na plus Nd into W. The W is the total depletion. If you recall, this is your the charge, this is your actually charge, the charge that you are storing, okay. And if you recall, this W actually can be written as 2 epsilon naught epsilon s by Q Vbi, because there is a reverse bias that you are applying here, plus Vr into 1 by Na plus 1 by Nd, right. So, this is depends on that, right. So, essentially what I can do is that I can say that your charge that you are having in the depletion is Q Nd, okay. If I look here, okay, is Q Nd Na by epsilon naught epsilon s into Wn. I mean that is because it is Na plus Nd into 2 epsilon by square s Vbi plus Vr into 1 by Na plus 1 by Nd, okay. Now, the capacitance is defined as the derivative of this Q with respect to Vr, I mean that is the applied voltage, right, Vr or Va. So, essentially this particular expression needs to be differentiated with respect to Vr. If you do that, you will actually end up getting epsilon naught epsilon s by W. You can do the math, this is farad per centimeter square, you can do the math, you will end up getting this. So, that is why your capacitance actually is the parallel plate capacitor only, and with more reverse bias, if you apply more reverse bias voltage, your W will increase, right. If your W increases, your capacitance will decrease. So, with more and more reverse bias, your capacitance also decreases. Now, you can of course choose to write the expression of W in a detailed form like I had written here, right. This detailed form you can choose to write, and then what will happen is that if you do a little bit of more mathematics around that, if you put this W as the detailed value, and if you take 1 by c square, right, if you just take as 1 by c square, the value will come out to be something like, if you do all the math, 2 by charge of electron epsilon naught epsilon s, okay, epsilon naught epsilon s by doping, say I am talking about one sided abrupt junction, which means I am having p plus very highly doped p type and very lightly doped n type, or relatively lightly doped n type. Then I told you that depletion is predominantly on the n side only, the depletion on the p side is negligible and we can neglect that. So, the depletion is predominantly on the n side only, it is called one sided abrupt junction, one sided abrupt junction, and the reason is called one sided abrupt is called because the depletion is only extending to one side, which is the n side, the lighter side. The heavier side may there is almost 0 depletion, okay, very small depletion. So, we neglect that. So, if you take a one sided depletion like, and this is suppose Nd doping and n side, this is very high doping, we do not care. So, in this kind of a one sided depletion region, if you do this capacitance voltage, put the W accordingly, then you will get an expression like this into the built in voltage of the PN junction. If you remember, every PN junction has a built in voltage, right, that is the built in voltage here also, plus V minus V applied voltage. This is the relation you will get. So, let us see again, you will get a relation like 1 by c square is equal to 2 by charge of electron epsilon naught epsilon s, the doping on the n side, p side doping does not matter because it is very high now, by the built in voltage minus the applied voltage. So, if you actually plot 1 by c square now versus the voltage that you are applying, then you will get a curve like this. It has a negative slope. The negative slope is given by this, minus is there, no, this quantity. So, the slope is given by minus 2 and the slope is negative of course, q epsilon naught epsilon s by n d. So, if you plot 1 by, so if you measure capacitance and you take 1 by c square and you plot with respect to the applied voltage, then you are going to get minus 2 by this. From this slope you can find out the doping on the n side. So, it is a very powerful technique to find out the doping. Okay. And you see this point, if you extrapolate, it will cut somewhere here, no. This point is where the y axis is 0, which means 1 by c square is 0. If 1 by c square is 0, then VBI equal to VR, which means this point is where your built in voltage is, okay, from this equation. So, the extrapolated value on this axis will give you the built in voltage. So, you can calculate the built in voltage also from the capacitance voltage profile. So, it is a very powerful tool actually, okay, it is a very powerful tool. And if you take a, you know, it is the same thing, if you take a derivative of this, of course, d by dVr 1 by c square, then you will end up getting minus 2 q epsilon naught epsilon s by n d. If you take a derivative of this, you will get the slope, and the slope is this, which is the same thing essentially I told you, right. So, capacitance voltage profiling is a very powerful tool or technique to find out the doping as well as the built in potential, and a PN junction actually behaves like a capacitor. So, you can take a PN junction, you can apply reverse bias, for example, you can apply reverse bias and you can sweep the voltage in a measurement tool, you can sweep the reverse voltage and you can monitor capacitance. So, you can actually get a C versus, you know, VR plot. Now, you take these values that you are getting in the Excel sheet, you reverse it 1 by C and then you square it, and then that will be your you know, that's 1 by C square versus VR plot, and that gives you the idea of you know, the doping and other things. Now, if you recall, your capacitance actually is epsilon naught epsilon s by W, and W depends on square root of VBI plus VR into many other terms are there, right. So, essentially your capacitance depends inversely as 1 by VBI plus VR, the voltage that you are applying. If your reverse voltage is large, then you can compare to built in, then you can even neglect that. So, this will be essentially VR. So, essentially your, if you are plotting the capacitance here and you are applying the VR, then this relation will go like this. This relation is basically 1 by square root of VR, okay. This is like that, it will go, okay. Okay, it will go like that. I think it probably will not go like this, it will go, the slope is positive, no. So, it will go like that. VR is, if the VR keeps increasing, then the capacitance becomes lower and lower. So, it will be like that, okay. That is what will happen actually, okay. So, this is all about capacitance voltage profiling of CV of a PN junction, and this is an important concept that you need to keep in mind, because in future when you discuss about many other things like BJTs or even MOSFETs, these capacitance voltage profiling and breakdown will become very useful and very handy in discussing those devices, okay. So, we will wrap up the lecture here today. We have now practically and virtually finished up PN junction. Whatever we needed to learn for the course we have discussed. There are many other things about PN junction like diffusion capacitance and small signal analysis, which we are not covering in this course. Those are becoming more advanced, those are sort of little bit more advanced topics. So, I have given you a flavor of how breakdown voltage relates to the PN junction behavior, how different band gap materials can have different breakdown, different power electronic applications need higher breakdown voltage, for example. I told you about the capacitance voltage profiling, that a PN junction is like a capacitor, there is a junction capacitance, and using that junction capacitance we have been able to extract the doping profile, the built in voltage and so on. So, these are very useful things that we are going to need as we discuss future devices, okay. So, we will wrap up the lecture here. What shall we discuss in the next class? From the next class we will start metal semiconductor junction. If you put a metal on a semiconductor, what is the junction and what are the properties? And before that we should ask ourselves, why do we need to put a metal? What is the necessity of putting a metal on a semiconductor? So, those things we will study from the next class, okay. Thank you.